Okay, hi everyone. Thanks very much for coming to one of these video abstracts. Today I'm going to be talking about permanent magnet optimization in the specific context of stellarators, but I'm going to try and show you that actually what I'm doing is more general for general permanent magnet optimization. And in fact, this problem has a sort of fundamental equivalence to sparse regression, which is the field that actually we've explored with the Cindy algorithm on a number of the other videos I've shown. So this is sort of an interesting way we've used the Cindy techniques in a very different scientific field and ported them over to this cool problem in plasma physics. This is work done with my amazing collaborators, and the work I'm showing can be found in these two archive articles that are working their way through the review process, and all of the results, methodology, etc. Can be found at that open source GitHub repository if you want to download the code and try some of this yourself. And we're going to see some cool geometric pictures of magnets oriented in different direction. So by the end of the talk, I'm going to hope you can somewhat understand these cool visualizations I'm going to show. So let's start with some basics, and then we're going to ramp up. So what's a plasma? Well, if we heat up a gas enough, a gas is just a bunch of neutral atoms, and if you heat it up enough, electrons pop off those atoms, and now we have positively charged ions, negatively charged electrons, and once most of the atoms have undergone this process, we call it a plasma, because it's mostly ions and mostly electrons. So it turns out more than 99% of visible matter is a plasma, and this is really important because the way that stars are maintained for billions of years is they squeeze plasma together, get ions really, really close, and they undergo a process called nuclear fusion. And this is a very energetically favorable process that researchers now for many decades have been trying to recreate on Earth so that we can have this sustainable, very powerful energy source. So one way we can try and achieve this is by basically making a bunch of plasma in some vessel and then squeezing that plasma to very high temperatures and hopefully higher densities with basically big superconducting magnetic coils. So we confine it with very strong magnetic fields, and this squeezes the plasma together very nicely. And it turns out there are many different ways and concepts for a potential fusion reactor for the future. So I'll just point out a couple here, but this is important because one of these concepts is called the stellarator. This is a cool concept because the plasma, it has some nice advantages. The plasma is very stable, and you can sort of pre-optimize the plasma and the coils in a really sort of systematic way. But the downside is that often it requires very complex engineering and tight tolerances on the coils and assembly of the machine. So it's just hard to make and can be expensive to make. And just to point out some differences, so you may have heard of tokamaks before. So this is basically you have some plasma here in blue. You sort of shape it in a donut, and you put on some big but sort of relatively simple, maybe circular coils all the way around, and those provide that strong magnetic field you need to squeeze the plasma together. And then the stellarator is a bit different. So it also, the plasma goes around in a donut, but now it's helically twisting as it goes around. And it turns out this extra shaping can be really helpful for plasma stability. If there's some, you actually do need some symmetry about the magnetic field. And then the downside of this is that you have to basically add a bunch of much more complicated looking coils. So you can see some of these coils are quite twisted and quite close together with another adjacent coil. So as I said, it has these beneficial physics properties, but these things can be very hard and costly to build in practice. So where do permanent magnets come in here? May not be clear so far. It turns out, so I mentioned stellarator coils are so complex that the cost can actually be prohibitive. Full-scale, sort of reactor-scale devices here can mean like $10 billion. So it's really a lot of money, and it really pays off to build coils and build a device that's sort of easier to manufacture and assemble. It turns out one way to do this is actually use permanent magnets in conjunction with simple looking coils, which actually allows you to reduce the cost and complexity of your design by replacing some of the gnarliness of those coils with just a bunch of cheap off-the-shelf permanent magnets surrounding the plasma. So this is the idea we're going to go for, and the strategy here is we're going to say, okay, there's some surface outside the plasma where we're allowed to place permanent magnets, and then we're going to try and formulate an optimization problem to figure out where are the best places on that surface for permanent magnets, and what should those magnet orientations be. And then we're going to sort of, and of course this is subject to giving the best possible plasma for various fusion metrics for how good it is at giving you a nuclear fusion reactor. So that's the idea, and I'll sort of pin that down a little bit more on the next slide. And so this is sort of a rough intuition, and as I said, we'll turn this into a well-defined optimization problem in a second. But just to visualize this, what it's going to look like is we have, again, so we have this helical looking plasma in this teal color, and then we have this magenta surface where we're allowed to put down permanent magnets, and that's going to sort of surround the plasma, and then we're going to figure out where on that surface should we put magnets and how should we orient them to sort of give us the plasma that we want with good physical properties. So what we do now is formulate it as an optimization problem, and in fact I'm going to show it can be formulated as what's called sparse regression. And if you've seen some of my other videos on the sparse identification of nonlinear dynamics, or SIND method, which is really popular for system identification, which is a different scientific field. This is actually basically exactly the same sort of optimization for that problem. So we can nicely port over a lot of algorithms and a lot of intuition for how to solve this problem. So let's get into that. So what we're going to do is we're going to say there's some big surface that we can divide into a grid of d possible locations for magnets, and then we're going to figure out which location should have which magnets. So we're just going to take as our optimization variables this m, and just say, okay, we're going to consider the x, y, z component of all of the d dipoles that you could place. So we're looking at all d dipoles and all their possible orientations. Okay, so that's potentially a very large number of optimization variables, but you'll see this gives us a nice formulation. So not only do we want to basically match some good physics properties at the plasma, but we're going to want some extra properties. So as I said, we're going to want to correctly generate the magnetic field at the plasma surface. This is a little technical, but the point is we want to get the physics right. We want to do a good job making a good plasma that has beneficial properties for whatever we're trying to do. And then we have some engineering properties on exactly what is the type of permanent magnet solution we're looking for. And if this will work, we need to do a few things. So it turns out permanent magnets cannot withstand like very high magnetic fields directly next to them. And so we need to actually not exceed some maximum magnetization. So the magnets are constrained. So I said that backwards. The magnets have a maximum magnetic field strength that they can produce. So we can't produce like 50 Tesla fields with these permanent magnets. We need to produce them with some realistic amount of magnetic field strength for the types of permanent magnets you can actually buy off the shelf nowadays. So there are some constraints we need to consider. We need to try and reduce the amount of cost for building these permanent magnet configurations. And one way is trying to use as few magnets as possible. So placing as few on that surface as you can. And the key word here is sparse. So we need a sparse solution. And then we also need these magnets, or we would like these magnets to be maximum strength. And the intuition there is that if we can choose a sparse set of maximum strength magnets, that would be a better solution than if we had many, many, many non-zero magnets, but they're all sort of weak. They only weakly contribute in their own way. And that will potentially require you to buy many weak magnets that might ramp up the cost of actually building these things in practice. So the key word there is binary. And then we would like magnets that are oriented in the grid directions. So we've built the surface with some grid in some coordinate system, and we want, in order to facilitate easy assembly in a realistic experiment, we need these magnets to be oriented along the grid directions, which allows us to sort of easily put these things in place when we build this. So grid aligned is the key word there. So it turns out all of these can be wrapped together into a full optimization problem that's equivalent to constrained sparse regression. So basically we're going to minimize some objective function over our optimization variables m, and the objectives are going to be this FB term, which is a linear least squares term in the m variables. And in fact, this actually encompasses all the physics that we want to include in our optimization. So all the physics is just a linear least squares in m. We can add some regularization with fm. So in this case, we add some Takhanov regularization. This just basically preferences sort of sparser solution vectors m. I won't go into, there's some subtleties there, but you can look at the papers for that. And then most importantly, we have the L0 norm at the end here, which basically counts up how many elements of m are non-zero. And so if we minimize that function, we're asking for a solution m star that has as many zeroed out elements as possible. So we're asking for a very sparse solution. So this is really where most of the sparsity promotion gets done. And then again, we have to subject our optimization problem to the fact that these permanent magnets can't have infinitely large magnetic fields that they generate. There's some bound, and that's the problem. So this is a complicated problem. It's linear regression in the first two terms, but then we have this L0 norm, which makes it sparse regression. And importantly, L0 norm is non-convex, so this is quite a complicated optimization problem. And in fact, this is a constrained optimization problem, and m can be like, the dimension of m can be like 100,000. So solving a 100,000 dimensional non-convex constrained optimization problem can be very, very challenging. Nonetheless, we have found some solutions. And some folks before us have also found some excellent solutions. So it turns out this can be solved well with gradient-based algorithms. Some examples are this famous algorithm that some other researchers and have built, and our algorithm with the relax and split, which we've designed off of this formulation as sparse regression. And then we also solve this with a greedy algorithm called GPMO. And this is basically solving this problem, but sort of in a clever and cheap way, which is you start out with no magnets on your surface, and at each iteration you just place the best binary grid-aligned magnet that most contributes to correcting your physics. And then at the next iteration, you imagine, okay, there's already one magnet, so now place the second magnet subject to that new configuration that again is binary, grid aligned, and most contributes to minimizing this FB where all the physics is. And it turns out these greedy algorithms work really, really well. There's a lot of details here, technical details and optimization details, but I'm going to now take you from this sort of how to formulate and just show you some results on some stellarators. So this Muse stellarator is so it's a real experiment. It's being built at Princeton right now, and we've taken the permanent magnet grid that they're using and basically solved this optimization problem both with our relax and split algorithm and with our greedy algorithm GPMO. And in both cases I should explain what you're looking at a little bit. So what you're seeing in this sort of neon green-blue color is the surface of the plasma, and I'm plotting the normal component of the magnetic field. And we want this to basically be 0 everywhere because we're trying to get the magnets to perfectly match the magnetic field at the plasma surface. But still, these errors are in the sort of 10 to the minus 3 range, and these are tolerable errors for these plasmas. So that's what I'm showing in these neon colors. And then in this red-blue color bar, I'm showing the different dipoles and the different orientations in R, phi, and theta. And then the dipoles that are 0, I've omitted from this visualization. So we're only seeing the non-zero dipoles on the grid. So that's what you're looking at there. And if you look at the different components of the solutions generated by these algorithms, you actually see that the relaxant split and greedy algorithm produce quite similar looking solutions, and both of them generate quite accurate grids and solutions that we can use to actually build these things in practice. So we're pretty pleased we found new algorithms and a new formulation that allows us to solve these kinds of problems. And just to drive this home, we repeated this on another stellarator called NCSX. And what we did is we looked at the errors in the physics, so FB, on a log scale. And then we varied the amount of what's called the effective volume. And you can think about this as the amount of space required for the magnets that you put down. So this is like sort of total magnet volume that you need for your solution. And what we were able to do is show that, for instance, famous and relaxant split can produce very high quality solutions for this NCSX stellarator at pretty reasonable values of this effective volume. But importantly, they can't do it with these fully binary solutions where you're placing a magnet that is grid aligned and full strength and no in between, right? We were able to get that working with sort of a number of weak magnets that sort of fill in the gaps importantly for this system. It turns out this grid is quite challenging to get an accurate solution with fully binary grid-aligned magnets. And so what we actually found is that with our greedy algorithm, which gives you binary grid-aligned magnets by definition, we actually are not able to beat like 10 to the minus 4 in this FB metric. And the way we dealt with that is actually built in some error correction into our greedy algorithm. So we go for 100 iterations and place 100 magnets. And then we do some backtracking on those placements to see, okay, did we place some bagged magnets? And we try and correct some of those mistakes. And when we do that backtracking, we see improvements to our greedy algorithm in this sort of neon green color, where we're able to get to beyond 10 to the minus 5 in FB. And this is actually the best binary solution generated to date on this grid by about 2 orders of magnitude. So we're really pleased, actually, our greedy algorithms with some basic error correction can give us fully binary, fully grid-aligned solutions that are the best that have been generated to date. Come on, clicker. Okay, so I've shown you how we formulated these things. I've discussed about how permanent magnet optimization is sort of, it's built on similar foundations to the Cindy algorithm, and showed you some very exciting results on some stellarators, showing that our algorithms can actually perform quite well. So to drive this home, we formulated a permanent magnet optimization as constrained sparse regression. This is really useful because this literature is vast. Many powerful algorithms exist to generate the solutions. And we have this really nice connection with the Cindy algorithm, which our group and other folks have a lot of experience with. In the pure binary magnet case, we actually showed in our papers that this optimization problem can be formulated as a variant of what's called the binary quadratic program, the BQP. This is also really nice because the BQP has been extensively studied, and so this actually gives us a really nice roadmap for continued improvements in algorithm design in the future. And lastly, we greedily solved these BQP variants to produce permanent magnet solutions that we actually have shown are higher performance and faster to compute than any previous algorithm. So we're really pleased that these, even though these methods are greedy, which tend to be suboptimal, we've actually shown that with these greedy algorithms you can get extremely good solutions on certain permanent magnet grids. So thank you so much for listening, and please be on the lookout for those papers. Check out the code if you're interested, and hopefully some more follow-ups in the months to come. Thanks again.